Welcome to the last chapter of my physical chemistry course. We're going to look at some complex reaction mechanisms. So it's going to be an extension of chapter 18, which was all about the basic chemical kinetics. Now we're going to look at how we're going to use those kinetics to try to analyze rather complex reactions. So bear with me. We'll work this through together. So the idea is that how do we know what's actually going on? And that's where our kinetics come along. We say, oh, in an elementary reaction, first order reaction is just one atom doing something. In an elementary reaction, a second order reaction could be two molecules of the same thing colliding and reacting, or one molecule of A colliding with one molecule of B. But depending on how the steps go, and what order dependence we have, we can see what's actually going on. It could be that A and B collide and immediately make C. Or it could be A and B collide, make another intermediate, and then sometime later they have to collide with something else and they fracture apart into C. And that's what we're going to try to understand. That we're going to look at individual steps and how the rate laws are managed in there and how the reaction order is dependent on the actual mechanism. Now, we could have a simple mechanism occurring in one elementary step, or it could be like 2, 3, 4 steps, and we need to reach the product. And so we'll deal with each of these. So let's look at the simple decomposition of N2O5 to NO2 and O5. So the reaction, as written, is 2 N2O5 goes to 4 NO2 and 1 O2. It could be written as a simple second order requiring one step, where N2O5 collides with another N2O5, and as they do that, all the N2O5s fracture off and oxygen links together. But it could have a much more complex reaction. At first, N2O5 reversibly breaks into NO2 and NO3. So this is a reversible reaction. This has to happen twice because we need 2 NO3s, because we have 2 equivalents of N2O5. Now, an N2O3, NO3 and NO2 collide to form an NO, an O2, and NO2. So NO2 is on the left and NO2 is on the right. It is important that it is there, but it doesn't actually undergo any change. And then finally, NO collides with NO3 to form 2 more NO2s. So that's a 3, somewhat 4-step reaction, because we have 2 of these first steps, then a secondary step, and the third step finally removes all the intermediates. Requiring multiple steps in the formation of intermediate species formed in one step and consumed in a later step, even the repetition of one or more steps. All this could be in our... So this repetition right here results in a stoichiometric number greater than 1. We have to do that twice because we have 2 N2O5. The only thing a reaction mechanism needs to have in order to be valid, that it has to be consistent with the experimentally determined rate law. So this first one could be right, the second one could be right. How do we know which one's right? We're going to look at the data. It has to match the data. How fast is this occurring versus how fast is that occurring? Is this a first order dependence on N2O5 or a second order dependence on N2O5? Is this step happening fast and suddenly we have a second order dependence on something else? And if the third step is the slow one, then we have it's dependent on these intermediates. So we got to really think about this. So the simple one, looking at the simple mechanism is simply going to be rate is equal to 1/2 N2O5 dt. Change in N2O5 dt, which is just going to be 1/2 K1 N2O5 squared. So, and that K1 could absorb the 1/2. Sadly, this does not actually match the data, so we can't use that. So that's not the true one. Now the complex reaction mechanism still starts the same. Well, we have the rate is equal to 1/2 dN2O5 over dt, but now N2O5 is going to be Kn2O5 to the first minus K -1 NO2 NO3. But what do we know about the intermediates NO, NO2, and NO3? What do we know about those? Well, we can use a steady state approximation on dNO dt, saying that's equal, the change in NO is equal to 0. So, and so set that equal to K2, NO2, and NO3. So that's how NO is formed, and minus K3, NO, NO3, where that is lost. So getting K3 and NO, NO3 to the other side, and then dividing by K3 and NO3, you cancel out the NO3s, and you're left with the concentration of NO is equal to 2 rate constants times NO2. Doing the same thing with NO3, another intermediate. NO3 is formed through the first reaction, removed through the second reaction, through the reversed first reaction, removed by the second reaction, and also removed by the third reaction. So moving all the NO3 terms to one side and dividing and factoring out and dividing them back over, we get that the concentration of NO3 is equal to a constant times the original concentration of N2O5 divided by some coefficients times NO2 plus a coefficient times NO, which when we plug in the coefficients for what is NO again, that's K2 over K3 times NO2. So that knocks out the K3, and that becomes K2 NO2. So we can add that in to get both terms of K2 to say concentration NO3 is K1 N2O5 over K minus 1 plus 2K2 NO2, which can be plugged back into our original equation. So the rate of this guy, now we have NO2, NO3, plugging back in. So 1/2 times K1 N2O5 minus K negative 1 NO2 times K1 N2O5 over K minus 1 plus K2, or 2K2 over NO2. So the NO2 is canceled out, and you have this nasty thing right here, but you can factor these guys together to say the rate of reaction 1 is K1 K2 over K minus 1 plus 2K2 times N2O5, which simply simplifies if we absorb all the K's together to a K effective N2O5. So despite all of this, the first reaction is essentially a first order dependence of N2O5. Now, if the first step is a slow step, then that's all it is. So we're also going to use some other things, approximations. This one, the first one we're going to use is called the pre-equilibrium approximation. So much like the steady state approximation, we can use the pre-equilibrium approximation to assist when we have reversible reactions. So consider the reaction A plus B goes to intermediate reversibly, and then it goes to products, which the forward and backwards reactions of the reversible step are much more rapid than the decay of the product. The steady state assumes K2 is very fast. Now we're assuming K1 and K minus 1 are very fast. So the premise, with that premise, we can state that equilibrium between the reactants and the intermediates is maintained during the course of this reaction. So before we even form a single P, we establish equilibrium between I and A and B. And the second I goes to P, we reestablish an equilibrium. So we never really leave equilibrium, even though I is slowly being consumed. So equilibrium will be maintained and the intermediate will decay to form a product. So how will we treat this? So this allows us to make a pre-equilibrium approximation under the assumption that the speed of the reverse reaction is much, much greater than the speed it takes to form a product. So, and then the first one, the steady state, we're saying the K1 is much, much slower than K2. Now we're saying K minus 1 is much, much greater than K2. Such that we can say that the rate of the product formation is equal to Kp times I. Now, this is true regardless of what approximation we're going to make. But at equilibrium, the rate of the forward and the reverse reactants are essentially zero, so that we can set 0 equals the forward reaction of Kf A plus B, A times B, and the reverse reaction Kr times I. So if they're at equilibrium, the change in I is essentially 0 from those first two steps. Instead of including the products as well, we're going to say those are equal to 0 and solve for I in terms of A and B. So we're saying that, well, I over A and B equals Kf over Kr, which is equal to our constant K, our equilibrium constant. Once equilibrium establishes, the decrease in I through the product formation is immediately corrected to reestablish equilibrium. With that in mind, we're saying that I equals our equilibrium constant times A times B. And thus, our rate of product formation is K of the second step times equilibrium constant K times A times B, or essentially K effective A times B. So under a pre-equilibrium approximation, the reaction is second order overall, first order with respect to each reactant. And while it can easily be described by K effective, it is not simply looking at the K forward or the K forward, so K1 or K2. It's actually a little bit more complex. It would be K1, K2 over K minus 1. Now, just looking at this in action. So the overall reaction mechanism, 2NO plus O2 goes to 2NO2. Experimental rate law sees a second order dependence in NO and a first order dependence in O2. While this could be a one-step trimolecular reaction, rate decreases with increasing temperature. So when we heat this up, we might expect this to actually speed up. But this could be like this, so it goes up one step. But another mechanism is K forward, K reverse, and 2NO breaks down and goes to 2N2O2 and establishes pre-equilibrium. Then N2O2 hits O2. Now, assuming we have pre-equilibrium, we can say that N2O2 is equal to Kf, Kr, NO2 squared. We would have had A and B, but since, not NO2, it's NO squared. So let me just fix that on the fly. Problems when you don't always check your You don't always fix everything right away. Okay. Okay. Okay, so we essentially have N2, the concentration of N2O2 is equal to KCNO squared. Then our reaction is Kp times Kc NO squared O2, which essentially sets the K effective NO squared O2. So essentially we have this situation where we can quickly establish equilibrium forward and reverse, and then once we get to equilibrium, it can jump over that last hill and it's not going backwards. While this also matches the experimental rate law, it explains why the rate decrease if the reversible combination was exothermic. So if this first step is the first step NO to N2O2 is exothermic, and you heat that up, that's going to make the reverse reaction. It's going to make the reverse reaction be favored. So I'm going to have more energy to push it back this way, and thus it's going to slow this down. So this can be exothermic overall, but this first step being exothermic, when you heat this up, it's going to make it harder to break it over. That's going to make it go backwards too much. So now there's another interesting mechanism. We're going to say the Lindemann mechanism. This was developed as a means to explain the first order dependence in a unimolecular reaction. How does a compound, just generically A, develops enough energy to undergo fragmentation, and experimentally it shows a first order dependence on A and only on A. So how does it magically react with it by itself? How does A get enough energy in the first place if it's not through some bimolecular collision? How does A just naturally shatter? Lindemann proposes two-step mechanism to explain this. The first is that A collides with a second A. So we just have a bunch of A bouncing around, transfers kinetic energy to make an activated A, which we're going to call A star. So A has enough energy to undergo A star has enough energy to undergo decomposition. So A plus A goes to A star and just another A. So essentially, two medium energy A's goes to a high energy A and maybe a low energy A, but we don't really care. But A star doesn't have to form product, as it can be deactivated through further collisions. So the following two reactions then occur. A star could react to form product, or A star could recollide with a low energy A to go back to two medium energy A's. So we have this reverse reaction. So if you look at the final rate expression, it will be simplified to the first order. So the rate of product formation is going to be K2 A star. But remember, A star is an intermediate, so we need to think about this in terms of the rate of A star. So we're going to make a steady state approximation for A star. Say that once it has the energy, it's going to start reacting. So A star, the change in A star is going to be 0. So how does A star form? K1 times A squared, and K minus 1, A times A star, and also K2, A star. So get all the A star terms to one side and divide by K minus 1A plus K2 to get what is A star. Plugging that in to our K2, A star, we get rate is K1, K2, A squared over K minus 1, A plus K2. So let's think about what this actually means. So in cases where the concentration of A is very, very high, so the K minus 1 times A is much greater than K2. So that essentially a big number plus a small number is essentially just a big number. And so the rate simplifies to K1, K2 over K minus 1, and the A's cancel, and you have a first order dependence on A. And all the K's essentially go to K effective. So we see a first order dependence on A. But at really low concentrations, where K2 is bigger than the effect of K minus 1 in A, the K2's cancel out, and you get the rate is equal to K1 A squared. So at really low, it looks like it's first order dependent, but over time, if you let it go long enough, it develops a second order dependence. So it essentially looks first order, and then something breaks linearity and jumps into second order once you get that tipping point. So we get a generalized, we can have a generalized Lindemann mechanism. So now if the second A is only there to give collisional kinetic energy, who's to say we can't make a different molecule, a non-reactive molecule? We're going to replace it with a generic M, which can be a non-reactive gas, it could be a product, could be anything. It could be a reactant. So most commonly, if it's in the atmosphere, it's nitrogen, because nitrogen is a pretty non-reactive gas, making up over 70% of our atmosphere. So just A plus M gives us enough energy, A star. So the overall rate simplifies to, we do the same thing. Instead of A squared, it's A times M. And instead of over A, it's now M down here. Once again, if M is a large quantity, if M is a non-reactive gas like nitrogen, K minus 1 times M is going to be much bigger than K2 on most cases. And it simplifies to A K effective times A, where M and M cancels out, because M is never going to decrease. The only thing that's going to change this would be the initial concentration of M. Because if I put nitrogen in there, nitrogen's not going to react. It's just going to bounce, 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 bounce. And it's going to stay there. So the only time this is going to change is if we put this at incredibly low pressure. So there's not enough gas molecules around to establish that K minus 1 times M is greater than K2. That's where we're going to stop this video. So, share. So let's keep on working on this mechanism in the next video. We're going to look at catalysis next. In the meantime, please like, please subscribe, please comment. I like to hear someone's actually learning something out there.